Hello and welcome to Some Assembly Required. The previous video ended with us showcasing that we can run the test program on a real CPU and verify it against the test plan. Of course, in the process, we also found a bug in the CPU implementation. And I mentioned that I'd really prefer to put a clear overflow instruction right at the beginning of the program. Except I can't do that because to do that would mean pushing everything down. And that in turn means manually modifying all relative jumps and making sure everything still points to each other. It'd really be great if we had a tool that would automatically allow us to do such things. And what do you know, such a tool actually exists. It's called Symbolic Assembler. Not only does such a tool already exist, but we actually have multiple assemblers to choose from. So what we need to do is somehow write our code for a Symbolic Assembler, and then take the output and convert it to the mem file we use to drive our test bench and test harness. I'm going to be using a symbolic assembler called VASM. The reason I'm using specifically it is because it's the only one I found that had wide support for variants of the 6502 CPU. In particular, it supports the CO2 variant, as well as the Western Design Center CO2 variant, as well as on the original version, the illegal instructions, which I'll probably cover in some future video. So I can be pretty sure that anything I'm going to need anytime in the future is pretty much covered by this assembler. The first order of business is to write a test program. Probably the first thing we want to do is write a reset handler. So let's do just that. What we want to do there is initialize the stack pointer. So the way to do it is that we load the X register with FF and then do transfer X to stack. Next, we want to start executing at an arbitrary location we'll call start. You can set its location to say 300. One way to do that is to push the start address into the stack and then do return from interrupt. This will also allow us to put the flags in a known state. So we load the most significant byte of the start handler to the accumulator and then push that to the stack. And next we can load the least significant byte to the accumulator and push that to the stack as well. Next, we're going to push to the stack the value that will go into the status register. So we can now set which flags will be set when the program starts. This way it will start at a known state and we won't have uncertainties like we had just now. I'm going to set the overflow to begin with, just to see what happens. Of course, we might as well define those flags so we can use them. Let's also define an interrupt and a non-maskable interrupt handler. At this point, let's have them not actually do anything. That will create an infinite loop, but so be it. Next, we need to set the interrupt NMI and reset vectors to point to our handlers. We're free to now start implementing the actual test program. Our original implementation started with a few no operations, followed by a few load A instructions. So let's do that. Of course, let's not use A9, even though that's an important address. We're using that in order to make sure that it's interpreted as an operand rather than an opcode. But still, let's define it symbolically. Let's put an operation at the end, just so we know where to stop. Let's see how assembly works. The program compiles and produces a file called aout, which has this output. And at this point, we can write a program to parse this and turn that into a mem file. However, I wish to use something which is a little more friendly and will allow us more control over the output. If we add -L, we're going to get a listing file. The listing file contains everything we had before, except it also contains the source code and the source file and line numbers. So it contains everything I need in order to create a much more readable memory file. So once again, Python to the rescue. As you can see, we have here the source program with file, source file and line number. And we also have the address and the value for each and every line of the source file. This format is readable by Xilinx code tools and of course by our program to drive the test harness. The only thing left to do is to automate the process. I wrote a Makefile that not only automates turning a .s file into a .mem file through an LST file in the middle, but also creates the CPU variant. This way I can tell the program that now I'm compiling for the Western Design Center variant, and then do conditional lines in the test program to have the program be written differently for different variants of the CPU, which is great. All I have to do now is type make, and we have our test program mem file and our listing file. Let's put that to the test. Now we can cycle through the commands and see what happens. So we can see the read of the reset vector, and we can see start execution. Here's our load X, here's our transfer X to S, here's our load A. Now the push A should push to 1FF, which is the top of the stack, which we set here in the transfer X to S. Next, we do load A 0 and push A. Let's give it another 20 cycles. And load A immediate of 4 and push A, which writes to 1FD. And we forgot the return from interrupt. Let's fix that. The good thing is that fixing is easy. So here's a reset handler. We need to add RTI. And now just make and rerun our IPython. So everything was in history, it was easy. And now we need to just rerun. Let's check that again. Reset vector, start executing, load A, push, load A, push. Let's give it 20 more. Load A 4, push, RTI. Now we can see that we read from 1FD 44, 1FE 00, 1FF 03, and we continue executing at 300. No operation, no operation, no operation. Load immediate 5, load immediate, load 0 page, A9, it reads from the A907A, no operation. And now you will notice that there's nothing that tells it to stop, which is fine, I guess. I mean, the test plan was supposed to tell it, but we want to push things to the next level. If we have to manually update the test plan every time we make a change, then the entire purpose of this, of making changes to the test program easy, is lost. However, we have here an authoritative implementation. Why not use that in order to generate the test plan? Here's the idea. Initialize the test harness as before, read the mem file and write it to the test harness as before, but now start executing the cycles and just write whatever it is the CPU is doing to the test plan. Now, this means we can simplify the test plan. The test plan before had, this is an opcode that writes, this is an opcode that reads. We can replace all of those with a single instruction that says bus access of this type to this address, reading or writing this value. That's it. Of course, there's some nuances around the beginning. I'm only beginning recording everything once we read from FFFC, that's the reset vector, so that the unknown state of the CPU at the beginning of the program will not affect our pass or failure. But this leaves us with a new problem which we did not have before. If we look at the old test plan, it contained two types of commands. Commands that test the input. So this is a bus operation, so it expects this cycle to be a bus operation of this op type, this address, and this data. Or this is an opcode, so that's the opcode type, number of cycles, opcode, fetch address, etc. These are commands that verify that the CPU is doing what it's supposed to do. But it also has a different type, that one of asserting. You assert a reset or you assert an interrupt. If we're switching to automatically generating this, we need some way to replace this with something else. We need to tell it that at that point in the program, we need to assert the IRQ line low so that the CPU will interrupt or not, based on whether it's been masked. So we need some way to do that, and we can do that in the test plan because we're auto-generating the test plan. Also, the very last command of the test plan says this is an end marker. If you've reached here without an error, the test has passed. Again, we need to replace that with something. What I'm replacing this with is essentially memory mapped I/O. I'm turning the test harness into a full-fledged computer. Let's look at the test program again. We define the 02 page, so that if the most significant byte of the address is 02, that's our I/O page. We define several specially handled addresses. So if we write to 200, whatever we write and only write, then it means the program finished successfully. Likewise, if we write to 2FA a value, nothing happens. But then if we write to 2FB a value, so if we write here 3 and then we write here 4, then 4 cycles after this write, then a MILAG of the CPU will go low for 3 cycles. So this tells us how long to keep it low, and this tells us how long in the future to do it. So this allows writing a test that is completely asynchronous with the handling of the signals to the test itself. And the same for the reset and the same for the interrupt. So now we can say, okay, our test is done by writing to the finished trigger. Of course, for that to work, we also need the generator to support that. In the generator, we test whether the most significant byte of the address is 2. And if it is, we're calling a class called memory mapped I/O that takes care of all the semantics we just mentioned. This way we know that if it says we're finished, we're done. So just store A or store anything to the finished will cause our program to exit. So now we can make and we can gen test plan. And here we go. This line means we need 11 cycles before we reach reading from the reset vector. And now we actually have line by line the bus accesses that the test program does on an actual Western Design Center CPU. So that's the read from the reset vector, that's the load X immediate, transfer XS, load A immediate, the push A with the write to the stack, and so on. So this is the execution of our program, which ends with writing to 200, which is the last command of the test plan. So at this point, there are 2 things we need to do. First, we might consider updating the program that runs this on the test harness Not really important because we're already running it on the test harness with a generator. And the other thing we need to do is update the simulation to support this new syntax, which I am not going to do now. Instead, I will be throwing all of this away and starting over. But that's for the next video. In the meanwhile, thank you for watching.